Okay, let's just see if people are joining now. Yeah. Great. Yeah, I think we can start slowly. Hi, everyone. Good morning, good afternoon. Welcome to our webinar today. We're very glad to see people joining. Today, we have a very interesting topic and a very impressive speaker. We're going to talk today about enabling greater geothermal economics through applications and technology. And today's speaker is Clinton Moss. And now Clinton has spent his entire career in technology and operations across multiple facets of the oil and gas and alternative energy sectors. Clinton is a serial entrepreneur and recognized as one of the leading industry experts in emergency well control, well intervention, well bore positioning, and responsible for various innovations in the magnetic ranging space. Clinton is currently the president and the CEO of Gunnar Energy Services, a technology and service business designed to support the industry's most prolific wellbore challenges in the energy sector. So if you ever wondered anything about wells, you are in the right place. And now I'm going to quickly introduce myself. My name is Margaret Krieger. I'm the IJ Head of Communication and Research, and I'm going to be a moderator for today. I'm joining you from, unfortunately, not so sunny Berlin, Germany. And let's see if our chat works good. Could every one of you please give us a few seconds and write the country or city where you're joining us from? The chat can be found in the black bar below. Let's see also if you can hear us and see us very well. If everyone could do that, that would be really great. Ireland, Texas, Guatemala, hi everyone. This is great. This is great. Indonesia, Canada, Switzerland, we're really international. Washington, hi Peru. Amazing. So guys, in case you have any questions, comments, feedbacks, please use the chat throughout the whole webinar, because afterwards we're going to take questions. We're going to have a short Q&A sessions. We've dedicated 15-20 minutes to answer your questions. So please feel free. And also, no worries if you, for some reason, will have a bad internet connection and something will go wrong. We will share a video recording with you, the link to the video recording, so you'll be able to rewatch it as many times as you wish. We also stream in live on Facebook, and so I hope everyone's okay with that. And Clinton, with that, I'm going to give my invisible mic to you. Ready?
Thank you very much, Margaret. I really appreciate the opportunity to speak today. I'm joining you from sunny Newfoundland, Canada. It's on the East Coast. That's a little bit of a joke that I call it sunny because the weather is something like Aberdeen, Scotland. It can be overcast and rainy and have snow, but thankfully today it's a beautiful summer sunny day. And I'm quite delighted to be here and to be able to present virtually with such a nice day outside. So folks, I will go through the presentation, and normally I tell people to interrupt me and ask questions as we go, but that's not the format today. However, I encourage you all to write down your questions. Any questions, I'm quite happy to get through the presentation and spend as much time as possible to respond. And if we don't get to your questions today, you can always email me or reach out to me directly. And I just love talking about this stuff, so don't worry about bothering me with whatever question, no matter how small. So I'm gonna go through just a little bit about myself and my company, but then quickly get to what we're here to talk about today, closed loop geothermal systems. But I guess more generally, how we drive the economics in the right direction to enable us to pivot, and in particular, to pivot towards this kind of ubiquitous closed loop geothermal that is more or less available in any geographical location, or most geographical locations, I should say, around the world. So that's why I'm excited to really talk about it, because it's not a niche or limited application that we're talking about. This could be scaled up and realized all over the world, I do believe. And we'll talk about that, and I'll make some references here in the presentation. So I'll introduce them myself quickly. I'm I've been in industry, basically, if we talk about it from a high level, placing wellbores subsurface for the last 15 years. It's pretty much been my sole focus since I've been in industry. And from the very beginning, it's not been limited to oil and gas, but all different sectors of the energy industry and civil and construction. I'll talk about that in a little bit. But basically, right out of school, I joined Halliburton Spearhead Drilling, and I ascended to the position of Global Ops Manager in Houston, Texas. For a year or two, I was a well control specialist with Wild Well Control. And of course, I'm just noting that I graduated from my home province, Memorial University of Newfoundland, from the university here. And kind of that's the educational background and kind of the basis upon which the rest of my understanding of how this stuff works was built. So it's fine to have all these jobs, but more importantly is what I've done with my experience. And I think it's critical to highlight that this is not my first time starting a technology development company. I originally started marksman ranging technology with some partners, and marksman ranging was meant to, or our goal was to develop magnetic ranging systems. And we went about doing that at various stages over the last 5 years. But basically, I sold and or developed for Scientific Drilling International these various magnetic ranging systems. So I'm certainly accustomed to how this stuff works. And the tools that I developed at Marksman that are owned by Scientific are deployed routinely all over the world. So I have a lot of experience with this. Now, it's not just from a management perspective, leading a team, although I did do that, but I'd like to say that I was down in the trenches. What do I mean by that? Well, I took part in the development process. I would solder these tools together. I would calibrate, experiment with them, and actually when they were ready, deploy them in the field at the rig site. So that real kind of hands-on experience has given me what I believe to be a very deep understanding of how this stuff works. And hopefully I can impart some of that or share some of those learnings with you in this presentation. So Gunnar Energy Services, and this is the last introduction slide, folks, before we get to something more interesting, is focused on these niche and specialized areas of wellbore placement that revolve around complex completion, and almost inevitably we will have to invoke some type of magnetic ranging in order to accomplish this. So we have engineers and scientists, and our focus is in this wellbore positioning space, and in particular as it relates to magnetic ranging. And we want to very rapidly develop fit-for-purpose technology for emerging challenges that we see in the marketplace, and eventually make our way towards being the leaders in wellbore placement. That's my strategic intent and my vision, and you folks can follow along and see if I'm able to accomplish that as the years go by. Okay, let's turn now to some background information that we need to cover in order that we have a true appreciation for the challenge of placing wellbore subsurface, and in particular, the challenge of placing wellbores in such a way so as to facilitate a closed loop geothermal system. That's what we're building up to talking about today, this concept of closed loop geothermal energy extraction. Okay, when we drill a well, you can see this picture on the right-hand side. When we drill a well or a number of wells from one common surface position, we represent them in this illustration you see on the left as just a line in space, and that's what we are told, or where the wellbore position is reported. But in fact, regardless of the survey method that's used, be it a magnetic or a gyroscopic method, all these methods have compounding errors, because what are we doing? We're actually integrating through the wellbore, all these various survey positions to give us a a downhole position, a three-dimensional position in space. And each one of the measurements that we use to calculate the bottom hole position, namely the measured depth, the inclination or tilt, and the azimuth or direction, have small errors associated with it. So no survey instrument is perfect. And these errors are compounding. So if we consistently have an error that repeats over and over again, and it may not be, it could be a random error or it could be systematic, well, then we have then accumulated this uncertainty, and these wells are not exactly as reported. So you can kind of see that on the right-hand side. We want the wells to all be spaced evenly. For example, in this illustration, all spaced evenly apart, you see on the left, but in fact, what is delivered is something more akin to what's on the right. So there are a number of techniques we can use to reduce these errors and manage these errors. And for conventional drilling, where we have a huge reservoir, let's just say a huge oil and gas reservoir, it's not absolutely critical, although it's preferred, but it's not absolutely critical that the wells be perfectly spaced. But there certainly cannot be any tolerance for that if we want to actually physically connect wellbores, okay? So the point that I'm making here is that this uncertainty is such and has the magnitude whereby completing or intersecting two wells together is not practical. It's not practically possible because the uncertainty is such that you would have to make multiple attempts at joining two wellbores while suffering this, this positional error. So summarizing very quickly, that's a lot of verbiage to explain simply that the wells have uncertainty in their position, and if you want to intersect one well with the other, it cannot be done. It's not a practical, reasonable approach to intersecting the two wells without some form of surveying. And I'll tell you what that form of surveying is here right away. This is more of an illustration of what I just spoke of. So when we account mathematically for the errors, you can see that, you know, the error, for example, in direction is usually larger than the error in the tilt or the inclination. So we have this ellipsoid. It's not a uniform error up and down, left and right, for example. So we have this ellipsoid of uncertainty. The way to think about that is that the well, this is typically modeled, this uncertainty, as a Gaussian distribution. And the ellipsoid then, let's say if this is a 3 sigma ellipsoid, if you drill 100 wells, 99.5 of them will be contained inside the area of the ellipsoid. And you can see by this illustration as well, the ellipsoids are growing. Now, for a 15, 20,000 foot well, the order of things, the scale of things are something like 150 to 100 feet, or let's just call it 30 meters of uncertainty in the lateral position of these wells. So obviously, if we have errors in the range of 30 meters or 100 feet, we're not able to simply drill another well and intersect it, because the other well that we drill also suffers the same compounding errors and the same uncertainty. So imagine two wells that are going to drill down and intersect each other. Is it reasonable to believe then that we can intersect them when the wells can have uncertainty between each other amount to hundreds of feet? That is certainly not the case. So we need another method to deal with this if we want to precisely space these wellbores, and in particular, if we want to intersect the wellbores. So there we have it. That is the issue, these compounding errors. That's a quick review of the errors and where they come from. And now we're going to talk about how we deal with this with ranging, okay? So what is ranging? Well, it's a relative position between 2 points in space. It's a vector quantity, so there's a distance and direction between the 2 points. And in this case, what I'm illustrating is if I want to know the position between these two horizontal wells that I've pictured, I could deploy a magnetic ranging technique, and it would tell me what the distance and direction is. Now, based on the surveys alone, we would think that the wells are placed, you see this vector, the black line with the arrow. And we think that the wells, based on surveys alone, are relatively positioned in the way that is dictated by their center point, the center of each respective ellipsoid. But when you perform this magnetic ranging, in fact, and I'll just click to the next slide, they could be on the outside edge of each ellipsoid. So you can see there's a discrepancy both in the distance and direction. The blue dotted line is where we think the wells are, and the black line and the two stars is illustrating where the ranging actually indicates that we are. So we could have, and we don't know precisely what wells contributed to the misalignment. It's probably both, but both have errors that we must reduce now to a relative, a geometrical problem, as opposed to this uncertainty based upon integrating from the wellhead position on surface. So the ranging allows us to get a downhole relative position between the two wellbores, a distance and direction. And these ranging measurements, they're not depending on the previous measurement that was taken. So we have that while there's error in the ranging measurement, it's not perfect, it is non-compounding. So it doesn't suffer from compounding errors like the aforementioned dead reckoning technique that I described, a survey, which is conventional surveying. And in fact, the error is proportional to the total distance away. So it's a little bit more complicated than this, but you could think about it that, you know, the error is some small percentage of the total distance. So if the total distance between 2 points is 100 feet, perhaps the error is 1 or 2 feet, maybe as much as 5 feet, but certainly somewhere around there. Now, as we use that ranging information to home in on the target and approach, and by home in we mean get ever closer, so to approach one well with the other. These errors become smaller just by virtue of the fact that they're, you know, some single-digit percentage of the total distance away. And at some point prior to intersection, the error has no practical consequence because, you know, let's say you're 10 feet away from the target, you have 1% error, well, then you're talking about, you know, inches. And certainly that's accurate enough to intersect a well. So this magnetic ranging then, or ranging in general, is determining this relative downhole measurement, which is the distance and direction between one point in space to the other. Now, there are several types of ranging, actually not several, a few, but the most prolific, the most common, the most widely used is magnetic ranging. So basically, we're going to use, we're going to analyze, rather we're going to sense, measure, and then analyze magnetic fields that are generated. And we will use that analysis to provide us with this vector quantity that we're after, this distance and direction between the 2 points in space. Now, magnetic ranging can, or whenever we think of any ranging, we want to think about how that's accomplished. And I like to distill it down to its two main components. We must always generate a magnetic field or have some magnetic field present other than the Earth's magnetic field. And we must receive that or detect it. So you have a source of magnetic interference or magnetic signal, if you will, and we have a receiver. So some type of instrument, typically an MWD measurement while drilling sensor or a wireline deployed sensor that is capable of detecting magnetic fields and the Earth's gravity acceleration, typically. And of course, the source, well, then that can be a number of different ways in which we can generate that magnetic field. Now, some examples of a method to generate the field is a rotating magnetic dipole, and I'll talk about that today. It's a fancy word for saying a bar magnet, okay? Or we could have some residual magnetism from a nearby casing, or we could even energize a wire or some other type of electromagnet to generate that magnetic field. But today, my source, or the source of the magnetic field that I will be discussing is a rotating magnetic dipole or a bar magnet, like it's on your fridge, for example, to keep your pictures in place, nothing too complicated. And the receiver will be a wireline deployed magnetic and gravity field sensor. Otherwise, it can be thought of as an MWD, or measurement while drilling sensor, deployed on wireline. So that's your source and receiver. Now, I'm limiting this conversation to just this one type of magnetic ranging. There are several. So, and I'm not suggesting that this is the only type of magnetic ranging that could be used for a closed loop geothermal application or other applications. But I use this one because it's fit for purpose for most closed loop projects that are being contemplated. So a little bit about closed loop systems. I'm borrowing this from Greenfire Energy. It's a paper that can be downloaded right from their website for free, and you can read it. And we see some interesting observations from the CEO, John Muir. And John has actually recently published this text that you see on the right-hand side of the screen. And basically what he's saying is that we want to use some of the oil and gas expertise that exists to look at the precise wellbore placement that is necessary in order to drill a closed loop system. He has illustrated, conceptually how that closed loop system will work. You see that in the illustration on the left. And he makes this very important point that I kind of referenced earlier, but I was kind of taking the words right out of his mouth. And it's basically this, that closed loop systems don't require this deep, hot, and movable liquid capable reservoir. But instead, if we have a dry, hot reservoir, which is found if we drill deep enough anywhere on the earth virtually, that we can circulate through some working fluid. And a closed loop circulatory path is ideal for that purpose. So if a closed loop system then can be designed and economically implemented, well then what we have is a scalable geothermal solution that could be used virtually anywhere. So that's what's really exciting, obviously, about this concept, that it's scalable. And more importantly, I think, or what really excites me, is that it's pretty straightforward to install. And I won't say it's not complicated, but I will say for people such as myself and other service providers that do this routinely, it is relatively straightforward and can be implemented on budget and on time. And I'll explain to you how we would approach this closed loop, or how it's been done, and how we could do it in the future, this concept of closed loop geothermal fluid circulation. So obviously, if you recall John's graphic, we want to have two wells, and we want them to intersect to form this loop. And the way that one would do it is drill two substantially vertical portions, and then they deviate to horizontal, and then the two horizontal legs would intersect one another. Now, those two horizontal legs, perhaps they extend, I don't know, 10,000 feet each, or 5,000 to 10,000 feet each, 3,000 meters, let's say, in the horizontal plane. Well, then they would accumulate tremendous uncertainty in their positions. And as I explained earlier, intersecting based on surveying alone is not ideal. So really, what we need to know is at the toe, or at the extreme end, the terminus of each well, what is the well's relative distance and direction from one to the other. So one leg to the other leg, and both are approaching each other with opposite directions. Okay, well, ideally we'd want to know that information right at the bit, where we're obviously affecting the increase in measured depth. That's where we're cutting the rock. So we don't want to know the distance and direction further back in the drilling assembly. It'd be ideal if we knew it at the bit. And here's a way that it has been done, and here's a way that we could do it, and allow me to explain. So we're going to use magnetic ranging, is what I'm proposed here, and in particular, it's a rotating dipole. So it's a rare earth magnet impregnated sub that exists between the bit and the bit box. In the sub, you'll have pre-installed these magnets in stacks. And we have then effectively a magnetic dipole. And what I'm illustrating that by these blue field lines that emanate from the sub. And this is in the drilling assembly of the drilling well. And as we rotate the drill string or pump fluid, mud, or circulate drilling mud or drilling fluid, if we have a motor present, of course, it will also turn that sub. So we have a dipole that's turning. That's a temporal magnetic field then that's been created. It's an oscillating magnetic field. The receiver, and I'll show more pictures of this later. The receiver then is a wireline deployed 6-axis sensor, and it's capable of measuring the Earth's magnetic field. It's capable of measuring the acceleration due to the Earth's gravity. And also it will measure the magnetic field of this rotating magnet. And it's that field, that measurement that we're very keenly interested in. So if we have then a source between our bit, or virtually a few feet behind our bit in the drilling assembly, and we get a distance and direction, more or less for all practical purposes, we have a distance and direction from the bit to the target. So this is ideal. If we were driving the school bus, we'd want to be sitting in the front seat, have all the kids behind us. Certainly we wouldn't want to be driving the school bus from the back, from the very last seat. So this is putting us at the head of the bus in the proper position, so we can make our adjustments to intersect both wells with information at the bit face. So that's what's a great advantage of this particular system. Now, we also can have software then that will take into account this ranging measurement and then automatically generate a new well plan that is designed to optimize our success of intersecting on the first attempt. So typically, there's one well plan issued when we drill a well, whether that be in oil and gas or geothermal or whatever the case may be, and all efforts are made to stick to the plan. Well, here, every time we take a ranging measurement, the well plan is ripped up, it's shredded, it's no longer valid, because remember, we're not where we thought we were. The ranging gives us that relative position that we need. And the well must then be replanned to intersect based upon that relative at-bit data. So this might be a little bit too involved for the webinar. And if you don't catch it the first time, don't feel bad, because there's a lot of angles and stuff going on here. And even today, I had to call the physicist to make sure I wasn't messing something up. So don't feel bad at all. But it's so beautiful. It's just so fantastic that I could not help but show you how it works. So it's not magic. It's so elegant a solution that I had to bring it to your attention. So please bear with me for the next couple of slides, if you will. Here's a little physics on a rotating dipole. Let's imagine, I showed you that sub with the field lines emanating out of it in the previous slide. So now I'm showing that sub on the left-hand side, and it's spinning about its long axis, and it is pictured in blue, and it has those magnetic field lines. And let me just pretend that I have the receiver directly above the sub. So imagine two horizontal wells. Here's the one well with the spinning magnet, and the other well's right on top. Okay, so that's what I'm illustrating here. So the rotating magnet is in blue, and in green we have the sensor. So it has the 6-axis data available from that sensor. Then I show a little tail on the end, that's the wire line. And now, if you see on the right-hand side, I'm showing my eye, kind of give a perspective. I'm looking down the wellbore. And then on the right-hand side is what you see. When you look down, you see that drill string, and it has this rare earth magnet in it, and on top of it is the sensor. And as we rotate the drill string, then we have this alternating or temporal magnetic field, and it is detected by the sensor. Now, if we plot that information, if we plot what we see on the two cross-axis magnetometers. You can see this elliptical pattern, okay? So look at the ellipsoid on the right-hand side of the screen. I've zoomed in on the data to show you that, in fact, there are thousands of measurements that are taken. You know, you might take 100 samples or 200 samples per second to properly characterize this. And when you plot the two axis data, the two cross-axis sensors, you see this ellipse. And that ellipse is quite informative. And the arrangement is so elegant because based upon just a geometrical observation of the dimensions of the ellipse, we can make meaningful determination of what our direction to target is or how we're aligned with the target. Now, to determine the distance, we just solve directly for the formula that you see for field strength there, the formula for there are some constants in there. Magnetic moment is present, and we have a distance as a cube value in the denominator. So finding out the distance not so hard. The direction to target is more complicated. But basically, the algorithm analyzes this ellipsoid that's been created by plotting the data, and it's dimensions of the ellipsoid that reveal if we're aligned or not. Let me show you the next slide what happens if we're on a collision course with the other well. If I have now the rotating magnet and then the sensor that are perfectly aligned, one's about to hit the other, what if we continue drilling forward? What do we see on the X and Y axis of the sensor? A perfect circle. Now, isn't that amazing? Just by inspection, if you have no ellipticity, once we plot these values, we know that we're on a collision course. Now, so we're aligned properly to intersect. Now, the operator doesn't visually look at this to determine this. The software outputs all these data, and an actual numerical value is output upon which that the new well plan will be based. But I just want to give you some intuition or understanding for what's happening. It's the fact that all these symmetries or geometrical relationships can be observed, and then of course the algorithm then can do a very precise mathematical interpretation of same to generate the ranging result. So basically, if you see a zero or a perfect circle, you're aligned to intersect. You're quite rightfully aligned, and intersection is all but certain. So that's enough of my physics class, regurgitating what the physicists taught me. We can move on now to more how we operationalize this, how it's used in the field. So there are a number of applications. This technology, I'm not the one to invent the concept of rotating magnet, but I'm certainly quite familiar with it and developed tools that do this before or have done it. And what we see is that, kind of the genesis for this is all these different applications that you see on the left-hand side of this screen. So there are coal bed methane intersections for dewatering and producing gas. We can have horizontal directional drilling and river crossings. So that's kind of what's referred to, but what is that? That's drilling underneath roads or obstacles or rivers or lakes or cities so that we can install water mains or fiber optic cables or whatever the case may be, pipelines perhaps. And we have a number of applications for oil and gas, and in particular, this system has been used, or this concept has been used for closed loop geothermal intersections. So it is ideal for that. Couple just observations on the right-hand side of your screen, the specifications. It's a fairly small sensor, so it can be deployed in tubing or in casing or in open hole. The rating, that's a critical importance. So the rating of the sensor is 175 degrees Celsius. And for some closed loop geothermal applications, that's certainly enough. So pressure and temperature certainly the system is capable. And in fact, in the past for closed loop that's been drilled, it was below those points. So, it proved to be ideal for that operation. You see some understanding of what the total detection range is. And just the fact that there are various sizes, of the rotating magnetic sub, if you will. So you can virtually, and you can upsize or downsize that rare earth magnet sub, goes between the bit and the bit box. So we have no real limitation on hole size, no real practical limitation besides that which is dictated by just normal drilling, hole cleaning, bit size, etc., casing size constraints. So that should give you some idea of typical performance from a that bit rotating magnet system. Okay, so how does this look now? We talked about why there's wellbore uncertainty and what causes that. I've made the case that we need to use magnetic ranging or some relative downhole measurement. I introduced magnetic ranging, and I introduced the concept of closed loop. So now we're going to put all these concepts together and see how we can realize or deliver the intended goal, which is this, access to hot formation, but dry formation all over the world via closed loop geothermal. How does one do that? Okay, well, another set of interesting observations from a key industry player. It's actually John, again, from Greenfire, and he says, just recently, in order for us to do or pursue closed loop geothermal, we need to concentrate on the following that you see on the left side. So first of all, cost. Cost must be reasonable. And what I'll say about that is magnetic ranging generally is, it's not the highest cost item. Certainly there's costs associated with it and the time to do it, but it's not the highest cost or anywhere near service that's going to be involved in drilling the wells. So while it should still be optimized and we should be as economical as we can and judicious in deploying the instruments, it's not the limiting factor that's going to drive the economics in an unfavorable or prohibitive direction. It was also remarked that we need greater surface area on these wells in order to maximize surface area contact. So when the working fluid is being circulated around, it picks up the most heat, for lack of a more scientific explanation. Okay? Greater surface area, more heat picked up by the working fluid. So can we drill large diameter wells with magnetic ranging? Absolutely. No issue there. We can upsize the apparatus in order to enable us to do that. Advanced completion methods. So I guess what's being referred to there is, advanced completion is in fact intersecting one well to the other. Can we do that with magnetic ranging? It's done all the time. Has it been done for geothermal? Absolutely. And can it be done then reliably going forward? Absolutely. Next, we say, is there measurement while drilling technology that will allow us to do this? Well, yes, there is. Magnetic ranging generally, or in particular, the type that I've mentioned here, magnetic ranging can work with any or most MWD systems. So most commercial systems, sophisticated systems that are available, not limited to any one or two or three service providers, but the majority of directional drilling service providers will have the ability to interface with the various magnetic ranging service offerings. So there's no limitation there. However, we still have to drill the well, and the well must be drilled in the presence of the pressure and temperature that is typically associated with geothermal. So we must be careful to select the system that can stand up to those environmental constraints, but generally the ranging is not the limiting factor there. Durability and repeatability. Well, in fact, this concept of closed loop between wellbores, it's been going on since the 90s, and a little bit of a history lesson. It was first done in order to allow for the control of a wild well. This is an oil and gas well that is uncontrolled release of hydrocarbons. And in fact, we would intersect, or has been, it was common practice, still is, to intersect one relief well with the target well in order that we control this expression of hydrocarbons on the surface. So U-tube or closed loop well bores, very deep subsurface, have been done since the early 90s. And there's no reason to believe then we wouldn't be able to continue doing this. This is not something that is completely novel. The concept of hooking up two wells together is generally well known or well understood, certainly from colleagues in oil and gas. And then John notes rightfully everything is HPHT. You know, I think it's fair to say the hotter the better. So, you know, 150 degrees Celsius, 175 degrees Celsius, that's routine in oil and gas these days. You know, in particular, there are regions of US land where they drill the shale plays that are, you know, commonly 150 degrees Celsius. So there's no real issue there. But now the limit on that, when you approach the limit to electronics, and I'll talk about that a little bit later, it's 200 or 175 and above. 200 is really the max for most systems these days. So we want to be cognizant of that when we're planning these wells. So in particular then, I'm just gonna zoom in on that last picture that I showed you. How do we close the loop? Okay, so we drill one leg from one direction, and we drill it to approximately the halfway point between both rigs, okay? And we withdraw that drilling assembly. That's the assembly that's on the right. Okay, we're gonna withdraw that drilling assembly and trip back in with just a bit that you see there, and the ability to orient typically in case we have some difficulty getting down an open hole. But then you'll have, you know, the bit, perhaps a motor or a bent sub, but then drill collars that are generally non-magnetic. We want them to be non-magnetic because we're gonna deploy the receiver of the signal, this ranging receiver via wireline. We're going to deploy it concentrically inside the assembly on the right-hand side there of this illustration. Now, when the receiver is in place and we are, you know, within ranging distance, so we drilled both wells, so they're, you know, more or less 200 feet apart, and now we're going to start doing our magnetic ranging. Well, then we've already installed on the left-hand side of this illustration the rare earth magnet sub. So we're going to have this temporal magnetic field then that emanates out in all directions in three-dimensional space, and it will be detected by the receiver that is directly behind the bit on the right-hand side of this illustration. When we generate the ranging call, we call it, or the ranging result, okay, then we can replan the well. And it would be the well that's on the left-hand side of the illustration. And we would plan then to intersect then directly one bit face to the other, and simply right before intersection, pull the working string off bottom slightly so as not to like physically have one bit chewing into the other one. There's no need of that, but we just pull it back slightly to allow us to re-enter open hole. So if you look at this illustration, and it's subtle, but what I'm showing is a misalignment in true vertical depth, a very small misalignment. So in this case, the assembly the drilling assembly, which is on the left-hand side, it would deviate up slightly. So we would drill up in order to intersect the well. The same can be said then for left and right, or if we drill up and left, or down and right, or whatever the case may be. We have complete three-dimensional control of the trajectory of the well that we're drilling, and then we can just regenerate a well plan in order that intersection is accomplished. Now, it is routine when we intersect wells, a geothermal well or any other, that we can freely trip the drilling assembly into the open hole of the well that we intersect. So what does that mean? It's something fantastic to see, actually. Once you intersect, we've essentially established hydraulic communication, so fluid can flow back and forth, but we also physically have a path through which we can advance the drill string now without any opposition of formation, because the well's been, you know, it's been previously drilled. So imagine then drilling for days and days and days, and then when you achieve intersection, you can just freely advance the drill bit into the well that you've just intersected. It's an amazing feat, and it is 100% conclusive evidence that intersection has been accomplished. So there's nothing left to doubt or guess once we've managed to close the loop, if you will. It is is certainly apparent to anyone that's on the drill floor watching this happen. Okay, so folks, my key takeaways here, quickly, because I know I'm going a little long, I think, is that magnetic ranging, okay, is going to be a requirement if we want to continue to drill these closed loop systems. Okay, so there's not, well, it need not be magnetic, although I recommend it, but a relative downhole position in 2 points in space from one well to the other will be required to deal with and drive out those errors, those compounding errors that I spoke of. Magnetic ranging in this application is relatively new, but that's for this application. Magnetic ranging is prolific, been used in industry for 20, 30 years. And like I said, first closed loop systems, not for the purpose of geothermal, but for the purpose of taming these wild wells. That's been done back as far as the early 90s. Expertise is essential here. I know that's easy for me to say as I'm the guy dispensing the expertise, but it really is, folks. It's complicated. It's not that the typical drilling engineer wouldn't understand or appreciate the challenges. She most certainly would, but it's not you don't want to do it the very first time without ever having done it, without the proper planning, the attention to detail, the engineering, and the oversight that's required. So what you do is when you put the effort in ahead of time is you minimize or give your highest, stated differently, your highest probability of first time intersection. If you fail to intersect, you don't want to be pulling back, cementing back, open hole side tracking. All this is unneeded cost, time, complication, and it's fraught with, it's kind of, the complication snowballs, if you will, if you don't get it the first time. You can really make matters difficult for yourself. So I highly recommend that folks, you pay attention and study this stuff and seek advice then when required. And a lot of the service companies that provide these services are certainly willing, with very minimal of any cost, to discuss how this works and some high level tips on how to plan the wells. A little bit more about looking in the future or what we have today and where things need to go, because what got us here cannot get us there. We need to always strive to do better, to advance things, and that's the purpose of my talk. What I'm hoping to accomplish is to give all of you listening the tools to understand these techniques and to unlock the key to economical closed loop installation, if it has not already been unlocked. But some things to keep in mind when you're planning and when we're encouraging our industry partners to continue R&D. Closed loop is certainly possible today, 150 to 200 degrees Celsius. It has been done, and it could be routinely done. But greater than 200 degrees Celsius, I mentioned this before, is really straining the limitations of downhole electronics and certain materials that are used in this drilling bottom hole assemblies. So we need further research and development there for sure, if indeed we want to drill, let's say, closed loop at 250 degrees Celsius, okay? And there's two ways to cope with this. You can increase the tolerance of the electronics, let's say, for example, to high temperatures, but you can also actively cool the electronics. And there are a number of companies that made some advancements there. In particular, I recall Baker Hughes did a presentation in Celle, Germany in 2016, about circa 2016, where they talk about prototype active cooling tools. That's where you physically use a process downhole in the sensor assembly itself to remove some of that heat that's affecting the sensors. And then, of course, in order for exploration, development, and investment to continue, we need to leverage expertise that exists in oil and gas. So some of the technical feats that have been accomplished in oil and gas, certainly we want to implement them if appropriate in geothermal. So leverage those existing, that existing knowledge so that we can make new production methods possible, or even to maximize efficiency on existing geothermal techniques. So let's, that's part of the reason why we're talking today, of course, is to make everyone aware, spread the knowledge, and so that someone to seed all these brilliant and clever people in the geothermal industry with some of the learnings from oil and gas, so that we can really push things forward in the right direction. So folks, that's pretty much everything I had. I'm sorry if I went a bit long. I can't help it though, when I get on this, I get talking, I get on these rolls, I could go all day. Hopefully you have some questions for me, and I'd be delighted to answer any questions that you have.
Yeah, Clinton. Wow. Wow. I have just one word. Wow. Thank you very much. Guys, do you understand what kind of experts you have here? Like, please take the advantage and ask the questions, use the chat. Also, if you don't have any questions, just give us comments. And what is the best insight that you sort of had today? That would be also very interesting for us to know. What I personally liked is your metaphors and this easy to relate examples, like driving the bus from the back seat or magnets on the fridge. That's really, really nice.
There you go.
I received already some comments that very, very good exposure on the closed loop system. So guys really like that. Maybe you can check your own personal chat, because sometimes people write privately and not in the open chat. That happens as well.
Okay. Let's see here. Okay, let's see. Okay, what effects are underway to eliminate the downtime associated with pumping or tracking a receiver down on the water line, incorporating a receiver into the drilling BJ? Okay, great. So typically I spoke of magnetic ranging requiring a source and a receiver. So we always have to think about it in those terms. So in the aforementioned case study, I said that we were going to have a source, which is in the bottom hole assembly, the spinning magnet, and the receiver, which is in the adjacent wellbore that's already been drilled. Now, how did the receiver get in place? Well, we had to trip an assembly back into the hole that we drilled, and we have to pump that receiver down the ID, the inside diameter of the drill string, and land it on bottom, okay? And there are time and costs associated with that. Now, how could we eliminate that time and cost? Well, there are other magnetic ranging methods that don't require to interfere or install anything in the other wellbore. But in this case, I'm talking about ranging from one open hole to the other, okay? So it's not ranging from one cased hole to the other. There are ways to do it with acoustic ranging, and so that would require only detecting in the well that we drill, and you're actually looking for the open hole in the other. So changes in arrival times from an acoustic transceiver as measured by acoustic transceiver. But for a head-to-head intersection, that is not practically possible, okay? And in fact, to say that we're going to avoid or completely eliminate the downtime associated with pumping or tractoring something in, via wireline, that's what Dustin asked. For this head-to-head geometrical configuration, that's not going to happen in the next 2 to 5 years. That's my prediction, because we need this look ahead. We need to be able to see what's happening ahead of us in order to accomplish this. Now, we could, Dustin, have the two wells drift into one another like this, but my understanding is that the reservoir people that model the thermal efficiency, they don't want that. So there are reasons to avoid it. But if we could alter the geometry and say drift one well into the other like so, then there are opportunities to eliminate having to deploy something in the other well. But for the configuration that I listed, it's not really practical. And if I said that I was overly optimistic that we were going to develop something that would allow that head-to-head intersection without putting something in the other wellbore, I would be misleading you. That's not the case. But having a source and a receiver in a common drill string, there's a lot of work being done on that. I'm working on it myself. But still, to range to an open hole in that configuration, the system that myself and others are contemplating would not address that particular configuration. But it's an excellent question.
I'm a bad moderator. You're reading your questions yourself, but I have one here. How does this procedure sit cost-wise? How expensive that is?
Yeah, so I'll give it to you in a scale of kind of like a fraction of the day rate for the rig. So typically on a rig that's going to drill that deep and long, the ranging will be, you know, a quarter of the cost of that rig, maybe a fifth, something like that. So it's a fraction of what you would what the cost would be to actually have the rig in place. It's a fraction of what it costs to have the directional drilling equipment available to drill the well. So it's you're talking about a you know, maybe a 30% increase on your directional drilling bill in order to be able to deploy the magnetic ranging technology that I'm speaking of.
Thank you. I don't know about you. I don't have any more questions here. We have a very shy audience.
Once the people rewatch the magnetic dipoles whizzing around and all the ellipses, maybe they'll generate some more questions and they can email me.
Yeah, they're very was a lot of information, and maybe it's hard to get it all at once, of course. But I have one last question, and please don't shoot me. The name Gunnar Energy, when we were discussing this with guys, it sounds Icelandic.
Yeah, so my uncle by marriage, he married into the family. His name was Gunnar Laurel. Finlanders pronounce it Gunnar. And in actual fact, he took to calling it Gunnar as well. But my uncle Gunnar was from Sweden, and he flew in the Second World War, and then he came to Canada and met my etc. But he's a very brave man. He, in the face of adversity, he was a real survivor. His plane was shot down. He was stuck in the Arctic for 9 days and survived in an igloo. And you know, I just thought, you know, it's very courageous man and very technically sound in terms of his piloting skills, etc. So I admired him, and for that reason, I named my company after him. And of course, the root of that name is warrior, brave warrior, and my uncle Gunnar certainly was that.
Wow, that's a very nice story.
Yeah.
A nice story behind. I really like it. Thank you.
You're welcome.
Yeah. Okay, so guys, I know you're shy, but maybe afterwards, when you rewatch it again, we will send you the link with the recording. Maybe you will have questions, and Clinton is very open. So please email him questions. We will also include, if you don't mind, your email or maybe a website where they can find the contact details.
Sure, yeah, it's Gunnar Energy Services.com, but we can distribute all that via email as well.
Yeah, we distribute that in the email.
My actual cell phone number is listed right there because I have emergency response with the company, of course. So you can call me anytime, and I'll just be here in Newfoundland enjoying the nice weather. You can reach it anytime.
That's great. Okay, with that, I think we're going to close. I would like to thank you, first of all, again, for a great presentation and a wonderful delivery, and all the participants that were watching us. Thank you very much. Stay safe and have a good day.
Thank you, folks. I appreciate it.
Bye.